Pleasure today to have to welcome David Schlegel from Lawrence Berkeley National Laboratory. David is a graduate of Princeton University. He did his PhD in Berkeley, then was a postdoc in Durham in the UK, and also in Princeton, where he then later became a staff. And at some point he moved back to Berkeley, to the LBNL, where he's now a senior scientist. He's archi-famous for his work on galactic extinction, and famous Schlegel, Finn Baker, and Davis maps that we all know and use and love. And he's a PI for BigBOSS, part of the Sloan Digital Sky Survey 3, and he's also the PI for BigBOSS, which is an ambitious project to expand on that, provide many more surveys using a bigger telescope, much powerful instrument, and he's going to tell us all about it today. David?
Thank you. Okay, does this work? Or you don't know? Okay, okay. Let me just try like this. Okay, thank you. Okay, thank you, Carlos, for the introduction. So I'll be talking about measuring dark energy from massive redshift surveys. I won't be talking about dust at all today, but if you really want to talk about that, I am around the rest of today. But it doesn't mean I want to talk about it. Okay. So what I'm going to talk about today is massive redshift surveys, both the question of what's interesting to do and then what's possible to do. So let's start with a little bit of history. So if you go back to the first redshift surveys done, so this was done by Geller, Hooker, and Davis in the 1980s, the CFA redshift survey. So this was a map, the first 3D map of just a few thousand galaxies that was made. This one was published in 1989. So a very pretty map. You can see the large-scale structure of galaxies. And essentially all the information in this map was contained in just taking the two-point function of this map, or the power spectrum. And so that's what I'm showing on the right. And so that's the original correlation function from the CFA redshift survey. And even though it distilled down to just that one simple plot, we actually learned a lot from that. Okay, so what we learned was that, as far as we could tell, the fluctuations from the early universe that grew into this galaxy map were something close to Gaussian and scale-free. And that it seemed like the CMB fluctuations were about the right order to explain the fluctuations that you saw in this galaxy map. Now, once we got more data on the CMB, there were some disturbing things that didn't quite fit. And so in particular, once you added the fluctuations seen in the CMB, so this is from the Kobe DMR experiment in 1992, this is now what the power spectrum looked like, where on the left, that's large scales, that's the CMB fluctuations. On the right is just newer data from these galaxy maps. And they didn't actually agree. And how much did they disagree by? Well, maybe a factor of 2 or 3. And at the time, for cosmologists, well, that was kind of good enough. It's like, oh, look, it all agrees to a factor of 3. This did bother some people. So the first explanation was, oh, galaxies, they're just biased relative to the underlying dark matter distribution, blah, 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 blah. That's all fine. Or maybe neutrinos had mass that was enough mass to actually be free streaming on small scales and suppress the power on small scales. That was another explanation. Or the one that no one believed was maybe there was a cosmological constant, and that would actually have this effect also. But that, so if I go on here, that was actually the right answer. Okay. So we did actually, we had enough information to learn that just from those early galaxy maps. what I'm showing now, this is our modern view of these same redshift surveys. So this is a movie made from the SDSS redshift survey. So this is the brightest million galaxies. And so I love this movie. I could spend the next 42 minutes talking about just this movie. Okay, so this is the beautiful thing about this is all real data. Every bit that you see there, standing outside my box. Every bit that you see there, each galaxy is put in the real three-dimensional location of that galaxy. And more than that, we've put in a little real color image of the galaxy in that location. Okay, so that's all real data. And not only does it create beautiful movies, it's good at movies, but there's a lot more to learn from this. Okay, so it's no longer the case that if you take a power spectrum of this map, that all you have is this one curve with a slope and a zero crossing. But there's a lot more information. So you take the power spectrum. Now we've zoomed out to this is the surface of flat scattering. And it's no longer the straight line, but there's a lot more information here. And in particular, the details of the shape of this curve tell you about neutrino masses affect that. Now we're zooming out to the control room of the telescope. In moderate scales here, there's a standard ruler that I'm going to talk a lot more about for the rest of this talk called the Baryon Oscillation Scale. And then as you go to the right here on the small scales, I've labeled that HOD, nonlinear growth. But that's a lot of information on small scales as well. Okay, so a lot more information. And in fact, once we're up to millions or tens of millions of galaxies, it's no longer the case that you can even just take this two-point function and say, oh, this contains all the information in the map. But there's actually more information than you have in a two-point function. So here I've just listed some of these out. I'm not going to talk about all these today. But there are some of these effects where you can fully describe it by the 2D function, and then others where you need higher order statistics than what's contained in that. Okay, and definitely not adequate if you're talking about 100 million objects. Okay, so this is where we are today. So if you take a slice through the observable universe, that's what this is here. And the outer rim here is the surface of flat scattering, microwave background. And what we did with Sloan 1 was we looked at the million brightest galaxies, and that's really just much less than 1% of the observable volume of the universe. And so it's contained in that little yellow sphere in the center. Now, our sensitivity to all these physics questions, that really scales as the number of modes that you can sample in this whole volume, or other ways of phrasing it, or as the amount of volume and the number of objects that you're sampling. Okay, so it's definitely an interesting thing to do, and the next question is what's possible? What can you map? And so if you just think about, what maps could we possibly make of the universe? It turns out, if you look at this, this is an image of the Hubble Ultra Deep Field, and you can look at the density of galaxies in here, and these are all objects showing in the optical. So these are galaxies where we know how to get a redshift of them. So in principle, it would be possible to get a redshift of every galaxy in this image. And you can say, well, what if we had this image over the whole sky and multiply it all out? And so it's about 140 billion galaxies. So that's how many objects there are to map. Yes, and then that would map about 50 billion modes. And this is where we are today. So this is just a fun exercise of you can just plot up the size of these redshift surveys versus time. So the first CFA redshift survey was a couple thousand galaxies. Today, we're at SDSS, which is 1 million galaxies. published in 2009, and you project forward, and we should be done by 2061. So you can compute there how old you'll be then. Now, one of the complications here is you can ask how big of a project that is. This is the number of authors in each of those papers. So you might not be doing this in Spain or the US, I don't know. Okay, coming back to present day again, I'm going to tell you about two projects. One that's happening right now called BOSS, which just started 2 years ago. And so this is part of the SDSS-3 project. And then I'll tell you about the next project that we're planning, which is BigBOSS. So let me start with BOSS. So this already is a large collaboration with a large Spanish participation. And it's designed around measuring this acoustic scale as well as we can. So you can make this list of all the interesting cosmological questions to ask. But then what we did was we optimized this particular project around measuring. I mean, you have to pick something to do. And so we optimized it around doing as well as we possibly can on this BAO feature in the power spectrum. And let me just tell you a little bit more about that. So I did see on your speaker list you have Daniel Eisenstein coming in a couple months, and he'll probably tell you much, much more about these things. So I'm just going to tell you a little bit. But what this is if you go back to the early universe, when the universe was just a plasma of protons and electrons, before they had combined, the sound speed in this plasma was quite fast. So it was the speed of light over square root of 3, basically. So anywhere where there was a perturbation in the early universe, you were projecting out sound waves, just like in this room, but at that speed. And that happened until the period of recombination, when the universe was 380,000 years old. And so all these sound waves froze out at that time. And because we know how fast these sound waves were traveling and how long they traveled for, we know exactly what this distance scale is. So this is something that we know from first principles in real physical meters. Okay, so this becomes our standard ruler. And what we've been able to do recently is actually see the same standard ruler in maps of galaxies today. So this is that same slice through the SDSS survey. And what this gives us is a ruler in meters that we can compare from the early universe to the universe today, or the universe wherever you happen to be making a map. Okay, this slide, this is a NASA slide here. So this is the NASA view of the history of the universe. So it starts out with the Big Bang in the upper left. It's very bright. Don't look directly at it. Then there was the period of inflation for some, what they say, tiny fraction of a second. Then you see the microwave background when the universe recombined at 380,000 years. Then the universe decelerated for about half of its lifetime, and then 6 or 7 billion years ago started accelerating again. And this is what we call dark energy, which we have no idea what that means, but that's what we're calling it. So the observable here, though, is we're trying to observe what actually happened in detail with this expansion. And from SDSS-1, we've been able to measure this BAO standard ruler to a precision of about 4% in the local universe. Now with BOSS, we're actually going out something like halfway across the observable universe, and we'll be measuring the same scale to a precision of about 1%. And so this is really an astonishing achievement that we're able to do this. So a little more history here. It's hard to measure distances and sizes of anything in the distant universe, right? And if you go back to Hubble in 1929, he was making measurements like this, but there was an error of about 700%. And if you go back even just 10 years to the key project for the Hubble, not Hubble the person, but Hubble Space Telescope, that was making measures of about 10% accuracy. Okay, so we have this standard ruler that we can look at in galaxy maps. And actually, it happens to be two rulers that we get to use at once. And that's because we get to use it looking both along the line of sight and perpendicular to the line of sight. So in the language of cosmology, you get to measure both a Hubble constant as a function of redshift and an angular diameter distance. And this slide is just to say that you really need a spectroscopic survey to do this, just to resolve what this BAO scale looks like. I'm not going to spend much time on this. Okay, so to make these maps, you can use any tracer objects that you want. And actually, if you go in the literature, there are lots of ideas suggested as far as what you could use as tracer objects. Some of them much harder than others. Okay, so there are even papers saying, oh, we should use supernovae to trace out the large-scale structure, which you could do, but are there any students in the room? Are there any students in the room? It's really not the easy way to do it. Okay, so the easy way to do it right now is definitely galaxies are the easiest thing to do. The microwave background has been used also, of course. And eventually, if you want to make maps in the redshift range of 5 to 10, then it's likely that you'd want to be using hydrogen gas. Okay, so with BOSS, what we're using, it's two kinds of objects. So first, it's galaxies, where we're making a map that goes to quite a bit higher redshift than SDSS-1. So on the left is an image of the SDSS-1 galaxies are in yellow. We have the sparse sampling of luminous red galaxies out to redshift of 0.4. Those are in white. But with BOSS now, we'll have a sample of 1.5 million galaxies out to redshift of 0.7, and those are the objects in red. At the same time, we'll be observing about 200,000 quasars beyond redshift of 2. And this was really a pathfinder experiment for us to see if we could use these quasars as a backlight to hydrogen gas. We'll just talk more about it here. Where along each line of sight to a quasar, you can take a spectrum of a quasar and get its redshift. And that's easy to do. So these 200,000 quasars, we can easily just make a 3D map of them. That works. But the real power in these quasars is the fact that each time you get a spectrum of a quasar, you can look at all of the absorption along the line of sight between you and this quasar, and then make a little one-dimensional map along the line of sight to each of these quasars. And so this is a well-studied field. It's called the Lyman alpha forest. Lots of people have been doing this for many years. But what's different here is we're doing this not just along one line of sight, but 200,000 lines of sight. And so that's a high enough density of all these lines of sight that you can use this to then reconstruct what the 3D distribution of the gas looks like. So this is what we're using above redshift of 2. Okay, I'm going to tell you a little bit about, so BOSS was partly a hardware project, so we did have to rebuild the SpectraS on the back of SDSS. So this is a slide, there's a lot in this slide, but what you see here, this is the whole instrument that we're using. So this is what's on the back of the telescope. So in the back of the telescope are these fiber cartridges with 1,000 fibers where you can point them at 1,000 objects at a time, and then those feed a pair of spectrographs that then split the light into blue and red, and so there are 4 different cameras. And what we sold this project was a targeted upgrade of, we're just going to change a couple things that we need to make the instrument better. In the end, there were a lot of those couple of things, and you can take an image of everything we changed in the Sloan spectrographs, and the other way to look at it is, what did we keep? And there are 2 lenses here somewhere that we kept. But it all works. Okay. But the most important things that we changed, though, were the gratings. So we changed from standard ruled gratings to what are called these volume phase holographic gratings, where at the time these were the largest gratings, such gratings made. Now Apogee has made larger ones. And the detectors were swapped out with some detectors that are much more sensitive in the red. So those were the big changes that we made to get better throughput on these spectrographs. Okay, so that all worked. We did have to do that construction project in about 18 months. And we completed it in time for first light in September 2009. So this is the first spectrum that we got. Actually, it was the first spectrum that came off the telescope where then there was a student sitting there saying, hey, isn't this a quasar? And we said, great, that's our first light image. So there it is. Since then, we've taken a lot more data. So this was just a few months into the project, actually. So this is data. I'm still not sure if I'm quite allowed to show this because this isn't public yet. But this shows a slice of the universe now from BOSS where, again, the yellow and the white is what we had from SDSS-1. And now the red points are the luminous red galaxies from BOSS, and all the blue points are all those quasars. Now, of course, dark energy is supposed to turn on around redshift of 1, but we just can't do it with this telescope. Okay, so these are what the data actually look like. So if you take a spectrum, these are not super high signal-to-noise spectra. So if you look at our galaxy spectra, by design, they're noisy. And the reason they're noisy is we wanted to get redshifts of as many objects as we could. So if these were really beautiful spectra, then we're doing the wrong thing. So we're doing the right thing, obviously, because these look noisy. So the black is the actual data. The blue is a best fit template. And what you can see is even though the black is very noisy, we can, with very high confidence, say the redshift of this galaxy on the left is 0.6. And actually, we know that to 3 decimal places. Then the quasars, they turn out to be quite easy to get redshifts for. So this is a quasar that's 22nd magnitude from BOSS. It's also very noisy. The redshift's easy. But then the hard part is it's not the redshift that we really care about, but it's all that Lyman alpha absorption that's to the blue, to the left of the bright Lyman alpha emission line there. Okay, but this all works, and I don't have results that I can show you yet on BAO and dark energy, but what I can tell you is that so far we've collected about 1/3 of the data, and it all agrees, the quality of the data agrees with what we're predicting it should look like from simulations. So there's a lot of n-body simulations being done at the same time to simulate what this BOSS universe should look like. And so a number of those have been done in Spain as well by the multi-dark collaboration. And if you look at, on the left here, this was the first detection of this BAO standard ruler back in 2005. where we expect to be when we finish this survey is this curve on the right, where, again, we'll be making these measures to about a 1% accuracy. Okay, so it's about a 1% precision measurement that we'll be able to make at redshifts of 0.3 and 0.6 from the galaxies, and then 2.5 from the Lyman alpha forest. So these are the projections of what this will look like. But the hope is that it won't actually look exactly like the projections, right? That we're actually going to learn something. Okay. And what I mean by that is that the expansion history might actually be something interesting that we'll learn from. Okay, so that's BOSS and where we are with BOSS. So since that finishes in just 3 years, we have to be looking at what the next thing is. And that's BigBOSS. And so this is the Kitt Peak 4-meter telescope. And the first thing you should notice is the sky is much more pretty at Kitt Peak. It really looks like that if you have the right glasses on. Okay, so BigBOSS, it's designed around a lot of the same science goals, but more so. So it's measuring dark energy from this BAO ruler, but really spanning this full redshift range where we go from redshifts of 0 to 3 and span that period where we think the universe went from decelerating to accelerating. But then also making measurements that are useful for determining the gravitational growth of structure over this period also. And then perhaps most interesting, non-Gaussianity from the early universe, so I'll come to that. The design philosophy of this project is to really optimize around just getting redshifts for these objects. So just like what we did with BOSS, we don't want the super high quality spectra, but we want a redshift. So the question is what we need to do to get a redshift. And to do that, the first thing you want is the simplest design that you can get, because the simple designs are what give you a high throughput and then allows you to do the largest survey. Okay, this is that slice of the universe again, where yellow is what we have today. Green is what we're mapping right now with BOSS. And what we hope to map with BigBOSS is everything in the blue there with galaxies, and then going out to redshifts of 3 and 4 along the lines of sights to even more quasars, and that's the stuff that looks like hair. Okay, so it's addressing all these same, slide there, addressing all these same questions again, but a design around, in particular, this BAO scale again, but then also measuring the effects of neutrino masses on these power spectra, and then early universe inflation from non-Gaussianity in these maps. Okay, so what this survey looks like is, again, it's a galaxy survey and a quasar Lyman alpha survey. But in this case, rather than 1 million galaxies, we're talking about 20 million galaxies. So it's a much bigger map, and it's primarily just much, much more volume than in BOSS. And then for the quasars, we had a lot of arguments about which quasars to look at, these quasars above redshift 2. In the end, what I said here is quasars above redshift 2.2. But in the end, we're just going to map every quasar in the universe. There are only a few million of them. Okay, so we're just going to put them in. So the ones above redshift of 2 you can use for Lyman alpha forest, but all of them are just useful. Okay. So when you look at this BAO ruler, BOSS will be measuring this from galaxies up to redshift of 0.7. But with BigBOSS, we know we can do this out to redshifts of 1.5 or 2. And so what we're designing this as is getting as close as we can to what we call the cosmic variance limit in this measurement out to redshift of 2, meaning that we're measuring it as well as the universe allows us to. So even with more galaxies, you wouldn't actually measure it any better because we're already mapping all the modes that have the information. And so now, rather than just 1% measures of what the expansion history looked like, now you're in the regime of 0.1% measurements. Okay, another exciting thing that you can do with these maps is look at any non-Gaussian signature in what these maps look like. And this is interesting because any theories of inflation tell you that there should be something residual in the distribution of matter in the universe that tells you something about what the inflationary period did. And so this is an important kind of constraint that you get from the CMB maps. But the problem with the CMB maps is a CMB map, it's just on the surface of last scattering. So it's just a two-dimensional map. And because it's just a two-dimensional map, you only have a finite number of modes that you can fit on that two-dimensional map. Once you start talking about these large three-dimensional maps, there are just many more modes. So the information content at getting at this information just becomes very much higher once you have a 3D map. So in fact, from BigBOSS, the projections are that you can do quite a bit better than you can even with the Planck satellite for non-Gaussianity. And indeed, it looks like you can get down to measurements that, well, at least some of the theorists say, okay, you're guaranteed to actually get a detection from non-Gaussianity. Now, I don't know what guaranteed means from a theorist, but maybe that means there's hope. Okay, the telescope to do this with, this is the 4-meter at Kitt Peak called the Mayall telescope. This is a picture of what it looks like today. This is what we plan for it to look like in 6 years. So we'll be taking this telescope and converting it to a 5,000 fiber spectrograph. So what this will have is corrector optics at the top of the telescope that give you a 3-degree field of view. Then sitting at the top of the telescope, 5,000 optical fibers. And then those fibers, they follow the yellow line here and then feed down to a bank of 10 spectrographs down in the basement. And in many ways, this looks like the Sloan Telescope in that it's really a simple high-throughput system. Okay, what really made all this possible was getting this 3-degree field of view with this telescope. And so it turns out that this telescope, it was designed originally to be a wide field telescope, but not a 3-degree wide field. But what that meant was that it's possible today with optics to actually correct to that size field. And so the first discovery of such a design was made by Mike Scholl in 2009. Using a Cassegrain design. Since then, there's been a family of models discovered by Ming Liang at NOAO, and that's actually what we've baselined now for the project. Now, when we discovered this, the other thing we did was we looked around and we said, well, let's look at every 4-meter class telescope in the world and see which ones actually could be used for a survey like this. And so here's the list of all the 4-meter class telescopes in the world. And you can go through. It turns out most of them cannot be. And the reason, basically, is that most modern telescopes, they're just made much more compact than the older telescopes, just because it's cheaper, I guess. But then the optics are faster, and then you really just don't have enough room to make a correction to give you a big field of view. So if you look at all these existing telescopes, there are 3 that are special, okay, and those are the 3 I've highlighted here in red. That's the Kitt Peak 4-meter, the Cerro Tololo 4-meter, and the Calar Alto 3.5-meter. Okay, so if anyone's ever going to shut down any 4-meter telescopes, you have to keep these 3. Okay, these are the most valuable ones in the world. So take a note of that if you don't write anything else down. Okay. Another thing that happened was Norm Blythe has retired. This was the man who plugged 1 million fibers for Sloan. So what that means is using these plug plate fiber systems, that's no longer feasible. So then we have to go to something robotic. And the requirements would be kind of stiff for Norm. So what our requirements are for BigBOSS is we have 5,000 fibers in the focal plane. We want to reconfigure those 5,000 fibers in under a minute. And Norm got pretty good at this, but I don't think he ever got that good. So the idea, though, is you take this focal plane of the telescope, the focal plane that's 99 centimeters in diameter. You divide it up into 5,000 hex cells, and then within each hex cell, which is about the size of my thumb, you have a robotic positioner that can move a fiber around. Okay. And this is what one of these systems looks like in practice on the Lemos telescope. So this is such a focal plane with 4,000 fibers. This focal plane, it's actually bigger. It's 1.8 meters. And so the fiber positioners, they're more like this size. And it turns out, engineering-wise, it is a harder problem the smaller that you make these. And so we need these little robotic positioners to be 12 millimeters center to center. And it looks like that's just about the size that's feasible to make. So in the picture here is one of our prototypes for BigBOSS at this scale. Okay, the spectrographs are being designed at LAM in France. These are 3-channel spectrographs. So Sloan uses 2 channels, meaning it divides the light into blue and red. Here we're dividing it 3 ways into blue, visible, and red. And the main reason for that is so that we can have a red channel that's resolution of 5,000. So I'll show you why that's important, but that's what drove this decision. The detectors, the most important channel for us is this red channel, and so we really want as high throughput as we can get in the red. And so we actually have an R&D program at Berkeley Lab right now to get as much throughput as we can on a red CCD. And so if you're interested in this, I can tell you more about this. But the short of it is the way to do it is to make your CCDs as thick as possible. And the reason is silicon is just becoming transparent to red light. But if you make the chips thicker, then you have more opportunity to catch a photon before it goes all the way through. Okay, so BigBOSS, what are we looking at? So I already told you lots of galaxies and lots of quasars. But really, we're just picking the easiest targets that there are in the universe. So whatever is easy to get a redshift for, that's what we're going to get. So in detail, when you look at this, below redshift of 1, the easiest galaxies to get a redshift for are these luminous red galaxies. That's what we're looking at right now. At higher redshift, what's happened is there's a lot more star formation out at redshift of 1, and so there are a lot of galaxies with bright emission lines. And so those are the easy galaxies to get redshifts for between redshifts of 1 and 2. And so that's what the spectrum on the bottom left is. You can see all these bright emission lines. So those are easy. And then the quasars, they're just always easy. Okay, the trick here, though, is to get a redshift of these emission line galaxies even when they've redshifted out to where the night sky is bright and you have lots of emission lines from the night sky. And so, sorry, this doesn't display very well. But the lower right here, this is a spectrum of what the sky looks like in the red. And it's just lots of OH transitional bands. So this is what I'm becoming an expert on right now, is what are all these OH lines. So the trick is to see a galaxy spectrum buried in this forest of lines. And to do that, you just need enough dispersion in your spectrograph so that you can see these emission lines between all these OH lines. Okay, so that's what we'll be doing, and we'll be making this map of all these galaxies in the northern sky over a period of 5 years, hopefully starting in 2017. But I told you there are 3 telescopes that you can get this wide field of view on. And so one of them is this Kitt Peak 4-meter telescope. It's the telescope on the left. Another one is this CTIO 4-meter. That's the telescope on the right. And it turns out these are actually twin telescopes. So optically, they're the same. So any instrument that you build for one of these telescopes, you can actually put on either one. So this actually gives us the option to build something for the Kitt Peak telescope, run it there for some number of years, and then complete a full sky survey by moving it south to the other telescope. So that's, we were lucky, right? Okay, so in summary for BigBOSS, this is designed to be this BAO spectrograph to get redshifts of all these galaxies out to redshift of 2, designed to get as many modes mapped in the universe as possible to get at this non-Gaussianity from the early universe. And this was not obvious to me or anyone else a couple years ago, that you could actually do this with a telescope that was only 4 meters large. But that's something that we're pretty secure on right now. And then I just have to show one slide here that has something to do with stars. Okay, so this is a simulation of a Milky Way-like galaxy. And one of the things that you could do with this instrument is, I mean, I hate to say it, but you could look at stars also. And it looks like you could look at of order 100 million stars over 500 nights with this instrument. So this really could be transformative as far as what we could learn about the Milky Way at the same time. So I'm not going to say anything else about that because there are other people here who know something about stars. Okay. So in summary, BOSS, which is running right now, this will be the definitive survey of so dark energy from BAO below redshift of 0.7. We're about a third completed right now. When we finish in 2014, it's these 1% measures of distances. BigBOSS then extends this out to redshift of 2 or 3 once you add in the quasars. And our hope is that we'll be addressing a lot of other questions like non-Gaussianity. And that these redshift surveys, aside from just measuring this distance scale, there's a lot more cosmology in there. So I'll stop there and take questions.
Are there any questions or comments? Could you elaborate a bit on how do you plan on recovering the 3-dimensional structure of the hydrogen in the universe from the Lyman alpha forest? I mean, how are you going to identify the lines? Are you going to interpolate in between, or?
Okay. Yeah, so that's a good
Because
question.
it's non-trivial, right?
It's not trivial. Okay, so this, I was going to say this is what these data look like. These data actually don't look anywhere near this good, but this is what good data look like. Okay, so you take a spectrum towards one of these quasars. Okay, so this is one of those spectra where it's been redshifted out to, this is about redshift of 4. So this is showing up right in the middle of the optical. This is the hydrogen 2-to-1 transition here. And if you look at the spectrum, then to the left, it looks much noisier. This is all the hydrogen absorption lines. So it's not noise. This is hydrogen absorption lines. When people started studying the Lyman alpha forest, the way to do this was to go to a big telescope, take a spectrum at very high resolution, and then identify each and every hydrogen absorption line that you could as a gas cloud along the line of sight. So you'd just be identifying gas clouds. So you can do that, but we don't need to do that. So to do that, then you're getting all this information on very small scales that we don't actually need. And it's a lot of the nonlinear physics. So we're not doing that at all, but we just say, essentially, the spectrum here, okay, so if you blow it up, so blowing up this part of the spectrum, it's this right here. And wherever there's a dip, that means there's more hydrogen gas. So you can essentially take that spectrum, flip it upside down, and then that's the map of your gas along the line of sight. And you don't care which ones are bound clouds or which ones are not bound clouds. And that's a simplification, obviously. So you need to do a little bit better than that. But that's basically what we're doing.
Okay.
My question is also related with these quasars. What's the density of quasars C2 for a square minute?
The density per square arc minute.
Oh,
that's a small number. Yeah. So the quasars above redshift of 2. So for the BOSS survey, what we know out to magnitude 22nd, there are about 35 of them per square degree. We don't actually get all of them because they're hard for us to find from the Sloan imaging. So we get about 20 per square degree. We get about half of them. Okay. And this is one of our problems in BOSS right now, in that we want to be targeting all these high redshift quasars. About half of them turn out to be stars. So in this data set from BOSS, we'll have 200,000 stars that we were hoping were quasars, but are actually stars. And we were talking about this yesterday. No one's actually looked at them yet, because there's you get this BOSS team together, and we start talking. I'm like, well, what's that? I'm like, oh, that's a star. I'm like, oh, what kind of star is that? Oh, I don't know. The conversation doesn't get very far. So anyway, so at 22nd magnitude, we pretty much know how many there are. Once you go fainter, that's not actually explored. So there are different luminosity functions for the quasars, but it's not actually bound by data right now. So I don't actually know the answer.
Okay, thank you.
You are trying to use now the 4-meter telescopes, if I understand well, because you want to enlarge the horizon of the thing you are able to see. And the way you are doing that is trying to reuse the possible available about 4-meter telescopes, changing the optics so as to have a large field of view, or the largest possible field, which is 3 degrees. Mm-hmm. I suppose that you are limited. Now you get to an end, because it's very unlikely to be able to have something similar in, so to say, a 10-meter telescope, which would be the next step. So I'm wondering, have you thought on the possibility of developing something like BOSS, BigBOSS, or whatever you can call it, for something with the design as the one that has the LSST? I mean, something which is going to map the whole sky, but with a different procedure,
Yeah, no, okay, so that's a good question. There are lots of questions in there. So let me answer at least some of them. So the first is, with BigBOSS, when we started designing BigBOSS, one of the immediate questions was like, well, why don't you just build your own telescope? And the answer to that is these existing 4 meters are actually, they're exactly what we want. So no one's built a 4-meter telescope like these for 40 years. And the reason is it would be very expensive to build them now. But we very much like, so these current 4 meters, let me just go back to this. Okay. So it's a physically large telescope. And so what we really liked about this is we could get not just this 3-degree field of view, but this 3-degree field of view at f5, which that's the right optical speed. So that means that for people who don't do optics, that means the light's coming in at angles like this. And that's a good angle for feeding a fiber optic and then for going down into your spectrographs. So it makes it a very nice system where the fibers, you can just have a glass fiber that's just polished. There are no lenses on it, nothing else. It's just a bare piece of glass, and the light goes right in. So it's a beautifully simple, high-throughput system. So this is a nice design. If you look at telescopes, well, any of these other 4-meter telescopes or LSST, the optics are much faster. So those, you're at f ratios of 2 or 1.5. So that means the light's coming in like this. And so you can't take the light like that and feed it into a fiber because it just reflects off the surface. It's coming in too steeply. So you can build fiber systems on those with micro lenses. You can do lots of complicated stuff and make it work. But that's not really what we wanted here. So anyway, so we're very lucky that this telescope actually works. So that's one of your first questions. Your other questions were what about beyond BigBOSS? So we do have to stay on track. We have to map them all by 2061, right? So you can ask, how are we going to do that? And whether you need 10-meter class telescopes or bigger telescopes or what you need. And well, I'm not gonna pretend that I have a short answer for that. But there are different things that you can imagine doing. And so one of them, for example, is, well, let's say I had a 10-meter telescope at La Palma that we could do something with, right? One interesting thing that you could do is these quasars that I'm talking about for mapping the Lyman alpha forest. Quasars, they're pretty sparse, so we're talking 40 per square degree. So it's a sparse sampling. Even for measuring dark energy, it's not actually the sampling density that you want. It's very sparse. There's a lot more information out there beyond redshift of 2. One way to get at that is to say, well, we can use more than just quasars for the Lyman alpha forest. We can use any objects. We can use galaxies. So you can imagine saying, well, galaxies, now you're talking thousands per square degree. So if you could, even above redshift of 2. So then you're talking about the possibility of doing something really transformative above redshift of 2, for example. They're good questions to think about.
We know from studying the backgrounds, the infrared background in particular, that half of the light emitted by stars in the universe is obscured by dust. So how do you deal with that in BAO studies?
Oh, a dust question. I hate those. So for these BAO studies, we don't actually care what tracer objects we're using to first order. So the fact that our sample isn't complete in some way really doesn't bother us, as long as these samples don't have correlations on scales of 100 megaparsecs. So if you had dust clouds that were 100 megaparsecs long, that would be a big problem. But as far as we can tell, all these sample selection complications are happening on much smaller scales. And I should say, though, that this isn't something that we can ignore, so that if you completely ignore these biases of where the galaxies are relative to where the underlying dark matter is, you would make mistakes. And in particular, the objects we're looking at right now, it's these luminous red galaxies. So they're a little bit special. So they're the most massive galaxies in the universe. We're saying, this is our tracer of the dark matter. And it's not exactly true, because they trace more where there are clusters. So you do need to have your simulations that actually look at those kinds of objects. And as long as you can kind of calibrate that out to adequate precision, it doesn't look particularly hard to do. So something we worried a lot about 2 years ago. Now there have been a lot of papers showing that it's actually pretty straightforward to do. I hope I didn't evade your question too much.
Okay, can we thank our speaker one more time?